In this last video for the conic sections, we're going to look at how to graph and write equations of hyperbolas. Starting out, notice that the standard forms are very similar to those of ellipses. The only main differences are that we have a subtraction sign, a negative sign, in the two equations. And this is what's going to indicate whether we have a horizontal, if the x squared term is positive, or a vertical if the y squared term is positive. The other parts of the equation are, as you may remember from the previous conic sections, the center, hk, and a and b act like the x and y radii of the ellipses, though we'll see that they're manifested slightly differently. So when we're looking at these hyperbolas, I mentioned the x and y radii, the a units left and right, the b units up and down. So those guys would normally have told us the vertices of our ellipse in the previous video. But now notice what they do. They essentially create boundaries for our hyperbola. The two asymptotes go through the corners of that rectangle I just drew and through the center of the hyperbola. And the hyperbola itself gets very close to those asymptotes as we head off to extreme values of x and y, here, 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 and here. Regardless of the direction of the hyperbola, the axis between the two vertices is always called the transverse axis. The other axis is the converse axis. Again, that's based on the direction of the hyperbola rather than the size of those two. We can also find the focal points of the hyperbola by using a variation of the Pythagorean theorem. Notice this is different than it was for the ellipses. This ensures that the c value is the largest of the three, c being the distance from the center to the focal points. So you have to go up and down from the center to find that. Also note that the slopes of the two asymptotes are going to be positive and negative b divided by a. That's rise over run. So run a units and rise b units, and that goes both directions, hence the positive and negative slopes. Notice this equation. What makes it different from the previous conic sections that we've discussed? Well, it should be obvious that we have a negative quadratic term. The previous quadratic term, the x, is positive. Because they have different signs, this is definitely going to be a hyperbola. I can't tell yet which direction it's going to go. We have to wait until we see the standard form equation before we know which direction the hyperbola will go. Like we did with previous conic sections, we're going to have to transform the equation from polynomial form into the standard form for a hyperbola. And just like that, we're going to group the terms together and move the constant term to the right-hand side of the equation. Then we're going to remove the common factor from each of these two groups, and I'm going to leave a blank to account for completing the square. Now notice what I just did with the y terms. I actually factored out a -1. That -1 could only cause problems when trying to complete the square, and so I've removed it. Makes life a lot easier. In the first blank we're going to have a 4, but remember that that is 9 times 4, so I'm adding 36 to the right-hand side of the equation. 9 is going in the y blank. Remember that's -1 times 9, so I'm adding -9 to the right-hand side of the equation. Now when we factor, we get x minus 2 squared times 9 minus y plus 3 squared. And all of this should equal 9 on the right-hand side. Just like we did with ellipses, I'm going to divide both sides by 9. Remember, that does distribute to both of the terms on the right-hand side of the equation. The 9's will cancel for the x terms, leaving x minus 2 squared, and I am going to put it over 1 because our standard form does have a denominator there, and y plus 3 quantity squared divided by 9. All of that is equal to 1. So we've now got this hyperbola into its standard form, and we'll be able to use that information to graph it. HK, the center, is going to be 2, negative 3. Plot that point right there. And remember that the two denominators, like they did for ellipses, represent this x and y radius. A squared is 1, that means the x radius is 1 unit. B squared is 9, so that means the y radius is 3 units. Now if this was an ellipse, the ellipse would be contained within those boundaries, but this is a hyperbola, which must exist only outside of these boundaries. And remember that these also help us construct our asymptotes. Going through the corners of that rectangle and through the center of the rectangle. Recall that the slopes of those two are going to be positive 3 over 1 and the slope of negative 3 over 1 for the other asymptote. Now, the hyperbola itself this time is going to be a horizontal hyperbola. That's because we do have the negative y squared term. So the vertices are going to be the right and left of the center, and the hyperbola will try to mirror those asymptotes. As it gets further from the center, it will get more and more linear and closer to those asymptotes. The last thing that we need to do is find our focal points by using the formula a squared plus b squared equals c squared. A squared is 1. B squared is 9, so that means c squared is 10. The square root of 10 is going to be equal to c. That's roughly 3.1 units. And so our focal points are going to be to the right and left of center, about 3.1 units. So right about here and here are our two focal points. And the coordinates of those two focal points are going to be 2 plus or minus the square root of 10, and then the y value of negative 3. Now we've completed all parts of graphing the hyperbola. We've shown the center point, the vertices, the two parts of the hyperbola, the slopes of both asymptotes, and the focal points. If we wanted to, we could also write the equations of the asymptotes by using point-slope form. Remember, they go through the center point and have slopes of positive and negative 3. So point-slope form for the equations of the asymptotes, y plus 3 is equal to plus or minus 3 times x minus 2. Again, the 2, negative 3 is the center point, and the slopes of the two asymptotes, positive and negative 3. Like we did in previous sections, now we're going to write the equation of the hyperbola based on information about its graph. I'm going to start by plotting the vertices, one at 2, 1 and one at negative 2, 1. Now, when you look at these two, you should remember that the center of the hyperbola should be directly in between the two. So the center point of this hyperbola is going to be at 0, 1. And that should help us start writing our equation. That tells us what h and k are. So we have x minus 0 squared over a squared eventually. And then we also have y minus 1 squared over b squared eventually. All of this should equal 1. And notice that the vertices are going to the left and right of the center. That means the y coordinate, or the y variables, will be negative in the standard form equation. Also notice that our vertices are 2 units from the center. That means A is going to be 2 squared. The other thing that we don't know right now is b squared. But we do have some other information about this graph. We know that the slopes of the asymptotes are 2 over 1. So that remember that the slopes of the asymptotes of a hyperbola are always positive negative b divided by a. We know that a in this case is 2, and we know that the slopes should be 2 over 1. So that means we're trying to find this b value only. We can cross multiply here to find b, and we find that b is equal to 4. We're going to take that 4 that we just found and put it back into the standard form equation and simplify when possible. X minus 0 squared is going to be x squared divided by 4 minus the quantity y minus 1 squared divided by 16 is equal to 1. So we've written the standard form of the hyperbola with vertices at -2, 1, and 2, 1, and with asymptotes of slope positive and negative 2 divided by 1.